Hey guys, so my name is Paul Murphy, and today I'm going to do a presentation on differential privacy. I absolutely love this topic, and I think it's incredibly useful. And so hopefully by the end of the presentation, you will all agree. So firstly, a little about me. I've worked as a software engineer for over a decade in a variety of roles, and my main interests are machine learning and data processing. And at the moment, I work as an engineer at VMware on an open source data processing framework called VDK. So here's a link to VDK. But we'll discuss VDK in much more detail when we go into the actual examples. So the goals of this presentation are that everyone should leave this presentation having a basic understanding of what differential privacy is and like why it's incredibly beneficial. And also, if you're looking to use differential privacy in the future, that you would consider VDK as your first option because it has great out-of-the-box support for differential privacy. Okay, so before we can get into how differential privacy works, we need to first discuss what it is and why there is a need for it. Okay, and to understand why there is a need for it, we need to talk about what is happening in the data space in the last few years. In the last few years, we've seen the emergence of big data. From making and validating business decisions to training machine learning models, data has shown itself to be vital to the operation of many businesses. This leads to companies trying to collect more and more data than ever, and to make their current data sets more easily accessible to others, which includes those in their own company and even those outside of their company. However, at the same time, we see that everyone is more concerned about sharing their personal data than ever before. And furthermore, countries are actually bringing in laws to make data sharing more difficult. For example, in America, there's HIPAA, and in Europe, there's GDPR. So obviously, this looks like it leads to a problem. We want to make data sets both more accessible and also less accessible at the same time. And it feels like a contradiction. However, if we dig into the details, we can see that there is a happy medium. What we want to make public in the data is actually we want to make the statistical patterns public, but preserve individual user privacy. And this is possible. Like, historically, what people have done with data sets is they just obfuscate PII, which is personal identifiable information. So maybe if people wanted to do analysis on credit card transactions, there might be some sort of data set where they've anonymized people's credit card numbers and some identifiable information, but made some sort of data set public. However, in fact, obfuscating PII is basically never sufficient. And it's also very rarely, like, without using differential privacy, it's very hard to prove that making the data set publicly available is safe. Whereas when we use differential privacy, we can make certain mathematical guarantees. So as an example of why PII obfuscation isn't sufficient is this governor on the slide. He was the governor in Massachusetts in the late 90s. And what he did was he decided to make the health records of public and state employees available to medical researchers so they could investigate the impact, for medical researchers to do whatever research they wanted. The government obfuscated patient names, addresses, and social security numbers. The governor assured the public that identifying individual patients in the records would be completely impossible. However, almost immediately after only a few days, a graduate from MIT was able to use the quasi-identifiers in the data to identify the governor in the data to prove to him that their current procedures weren't secure enough. Like, I think that's so amazingly cool that what they were able to do was join it with other data sets and, even though, like sometimes even though there's not a unique identifier in the data, there's these things called quasi-identifiers. And a quasi-identifier is a data value that doesn't identify an individual on its own, but can identify users in combination with other quasi-identifiers. So basically, the point here is don't be like Bill Weld. Make sure you use differential privacy instead of just doing PII obfuscation. So this is where differential privacy comes into play. Differential privacy is a technique used to protect the privacy of individuals when analyzing or sharing data. It's a mathematical framework that aims to provide strong guarantees that an individual's data remains private, even if it's used in large data sets or combined with other data sources. And the basic idea of differential privacy is to add random noise to the data before it is analyzed or shared, which makes it much more difficult for an attacker to identify the specific data of an individual. The noise is added in a way that preserves statistical accuracy, meaning that the analysis that researchers can perform on it will still be meaningful and useful despite the added noise. Okay, so within the conversation about differential privacy, there will always be three main actors. There's the owner of the data, which is the person to the leftmost on both rows. Then there's the curator of the data, and there's the analysts of the data. In the previous slide, sorry, can you guys see this will be the owner of the data, this will be the curator of the data, and this will be the analysts of the data. In the previous slide, we discussed medical records being released for research purposes. In this example, the owner of the data is the person whose information is in the table. So obviously, you own the data, you add a row to the database. That would be, if you smoke, if you had cancer, what age you are. The curator of the data is the hospital who would own the database. In this example, the hospital that owns the database, obviously. And then the analysts are the researchers trying to identify patterns in the data. Perhaps they're trying to identify how helpful drug A is on preventing cancer or something along those lines. Now, in this example, we do trust the hospital with our personal data. Like, we want a doctor to be able to see accurate information about us. But even though we want the doctor to be able to see accurate information about us, that's it. We want to be able to get good medical advice based on our accurate information, but we don't really want them giving it to other people. So in this example, we do trust the hospital with our personal information, but we only ever want our doctor seeing it. We don't want outside researchers being able to see our raw data. And so this is the bottom row. This is called global differential privacy, where we trust the curators but not the analysts. Sorry, just 1 second. So another form of differential privacy is where we don't trust anyone. For example, as an example of this, it might be if researchers want to know if people smoke. Obviously, everyone wants to give researchers the truth because they might be beneficial in making discoveries that will help smokers and non-smokers alike. However, people might not want to divulge this information because if you are a smoker, you would be concerned that this information will be used against you in the future on life insurance policies, and etc. However, with local differential privacy, we can actually ask people to tell us the truth if they smoke. But before we ever save the real value, we would add randomness to the results. So in the saved results, some who smoke will be marked as not smoking and vice versa. This would always give an individual plausible deniability and would encourage them to answer truthfully, resulting in researchers having a data set with noise but still statistical patterns. Today we are going to focus entirely on local differential privacy. So this will be the top row here. We're going to focus entirely where you don't trust anyone, you don't trust the hospital and you don't trust the researchers, but you still want to provide, you still see the value in providing information to them. So, but the reason that I've discussed global differential privacy as well is because if you go and research this on your own in the future, you need to know that's kind of the fundamental split between in differential privacy. So, sorry, just 1 second. Okay, so here we can see this would actually just be a normal MySQL instance or a normal Postgres instance. And people would just run queries on it as they see fit. It would be completely normal to users, where we would have added the noises before we ever saved anything to the database. So the query pattern looks the exact same. Whereas in global differential privacy, the MySQL query would almost be modified to add noise to the result if you did a count or something along those lines. So there are multiple techniques in local differential privacy. You almost need a different technique for each data type, really. So the first technique we're going to talk about is random response. Random response is used when the data type of the results we are trying to protect is Boolean. For example, do you smoke? It's either true or false. And random response is ideal for handling questions like this. So basically, I just want to go to the example because the pseudocode is quite, or this code is quite good. So basically how it works is before we answer, we flip a coin. If the coin is heads, we answer truthfully. But if it's tails, then we're going to flip another coin. And if the second coin is heads, we will return that we do smoke. And if the second coin is tails, we're going to return that we don't smoke. So it should be obvious that only 50% of the data in the data set is actual true information, but 50% is pure noise. That's assuming an unbiased coin. I hope everyone can see that. So it's just basically two if statements. First coin flip, if it's heads, answer truthfully, and second coin flip, if it's heads, answer truthfully as well. If it's tails, answer false. Obviously, we can use an unbiased coin. When the coin tends towards giving the tails probability of 0, then we are going to preserve the entire data set with no noise, because the coin is biased towards heads. It'll always give heads. We will always answer truthfully. But individuals' privacy is not guaranteed at all, because we've basically returned all the truths. When someone looks at the data set, they'll say, oh, there's like a 99.9% chance that the value saved in the database is the truth about that person. Whereas we could also send the probability of tails goes towards 100%, we preserve every single individual user privacy almost with certainty, but also we've lost our entire data set to pure noise. So there are really elegant formulas for comparing differential privacy algorithms, even across local and global differential privacy. But we're not going to go into them today because they're just outside of the scope of this presentation. They take a long time to dig into and understand, and they're very technical. But we will include links. There's actually links within our code to them for where we pulled the, where we've pulled the logic from, which will have be blogs on that specific technique. And we have links at the end of this presentation for anyone who wants to follow up. Okay, so the next differential privacy algorithm, I'm sure if some people have questions at the moment, we'll have a question, we'll take questions in just 1 minute. So the next differential privacy algorithm we're going to talk about is Unary Encoding. Unary Encoding is used to add noise to the data type when we are trying to protect, when the data we are trying to protect is of enum data type or enum-like data types. This means that there's a finite set of values that the results can take on. An example of this might be people's blood types. Just for anyone who doesn't know, there are only 4 blood types, and we know them ahead of time. There's A, there's B, there's AB, and then there's O as well. So now again, researchers are asking for people's blood types for research. You again probably want to give an honest answer. So you might want to answer because you know it'll help the research, but you might be concerned that divulging this information could make you more likely to be asked to give blood during times of crisis for the country, and you just don't feel comfortable giving away your personal information. So in this case, we would use unary encoding to hide the individual's user's details. Unary encoding is more technical in how it works compared to random response. Well, and before we understand even how unary encoding works, we need to understand what one-hot encoding is. People from machine learning will definitely know what one-hot encoding is, but I'm just going to go over it quickly because if we don't do that prerequisite, everything else won't make sense. So one-hot encoding is a way of representing categorical data or enum-like data in a vector of bits or booleans. I think I like this photo of it, actually. I think it's quite good. So in this vector, only one value can be set at a time, and the size of the vector is the number of categories or number of values in the enum. So in the blood type, there are 4 values, so the size of the vector would be 4. This example is the same as well. There's 4 values, so the size of the vector is, no, sorry, there's 3 values here. Apologies, it's not the same. For the blood type one, there will be 4 columns here. And this is only as 3 examples. We know them up front. There's red, blue, and green. So if red is set, so to represent the first value using the vector, we would set the first bit in the array, and then we would leave all the rest as 0. So this would be 1, 0, 0, obviously. To represent the second value, it would be 0, 1, 0, 0. Third value, 0, 0, 1. We can see it for red, green, and blue. Red is represented by toggling the first bit, blue toggle the second bit, green toggle the third bit. And then again, obviously blue here, just toggle the same bit that you toggled for blue previously. Okay, so we first of all encode the data like this for our blood type. And then we distort the information a small amount. We have these functions called perturb, which just sort of randomly flip some of the bits within our one-hot encoding. How much bits we flip? Obviously, the more bits we flip, the more we preserve individual user privacy. So again, it's that trade-off. But the more bits we flip, we add noise. We add noise, and the data set becomes less valuable. In unary encoding, there are 2 parameters for toggling the privacy and noise traits based on how private and how much value you want to retain in the data set. So what we do is we perturb the data using these P and Q, and then after the data is perturbed, it is saved to the database. And then we are on the save rows saved in the database. We are afterwards able to perform aggregations. There's an aggregation function that also comes packaged in our project, which afterwards you can use to aggregate the results. So looking at it, you'd be able to say, 30% of the population of O blood type, or 25% have the blood type AB, etc. So that's how unary encoding works. And again, there's elegant formulas for comparing these with other algorithms in the same space, but we are going to skip them today because, yeah, like they're very technical, but also I don't think it adds much more, makes it much more interesting. So just a quick recap. What we've done is we have discussed local differential privacy and global differential privacy, but we focused on local differential privacy, where we add noise before saving into the storage layer, which could be like a MySQL instance or a Postgres instance or anything, even a file. We've discussed two different techniques: random response, which is used for Boolean data types, and unary encoding, which is used for enum-like data types. Okay, so it's very important to remember these details because this is what we'll be implementing in the next section. So I've previously presented this to my team, and I've gotten 2 questions that I can answer first, and then I'll take on questions from the crowd, from everyone else, if they like. So one question I've been asked is, how is it that we add noise and then we're able to get back to the original? Sorry, let me just. So I've been asked 2 questions. The first question is, what if we look at a subsample of the data set, or if we're streaming in the data set and we only take a partial view of it? Like, there's certain parts of the data set aren't more noisy than others. Looking at a small sample of it it'll contain kind of half the noise always. But it is important to notice that because half the data set is noise, if you thought you needed 200 people to give you representative statistics in a normal data set, you need to more than double it if you're using differential privacy with the kind of unbiased coin, and if you're using random response, because half the data set is pure noise, so that's corrupting even some of the real data. So random response is really good, but you need a lot more data. Yeah, does anyone else have any questions?
I haven't got any more that come in the chat at the moment.
Okay, perfect. Cool. Sorry, I'm just trying. Just give me 1 second. I have another question that I've been asked before that I would like to address, which is the question was, how are we adding noise to a data set but then recovering the information later? And we're not recovering the original information. Like, the original information would be kind of rows in a database that says smoker, non-smoker, smoker, non-smoker. We never recover it where we feel comfortable saying who's a smoker and who's a non-smoker. What we recover when we do the aggregate functions at the end is we recover a high statistical, like, so beforehand you might have said, well, 40% of people are smokers. And when you apply the noise, we can still say 40% of people are smokers after we do our aggregation function, but we've lost no idea which of the people are smokers. Okay, so I'll move on to the next section now. Okay, so now we're going to discuss VDK. And so VDK is an open source software development toolkit designed to simplify the development of data intensive applications. It's the product I work on in VMware. And so, as we can see, VDK aims to assist in every step of the data processing journey. It eases difficulties associated with ingesting, transforming, and exporting data. As a user, you can focus on writing just the business logic of what you actually want to do, and we will handle the rest. Jobs can be written in Python or SQL. And so what do I mean by handling the rest? Well, we handle the operations side of running a data job. For example, where does it run? When does it run? How are failures and history managed? How is everything kept track of? We also handle the more tedious parts of coding, like connecting to a databases and abstracting away the nuances of connecting to different storage layers. We provide one clean interface for ingestion, which can be used regardless of the underlying data layer. If you're using MySQL, Postgres, Trino, Impala, the code will always look the same. So here, let me just zoom in. So here's a comparison of code written without Versatile Data Kit and code written with Versatile Data Kit. in the comparison, we can see that without VDK, a lot of boilerplate code needs to be written to connect to the database. So here we can see that we have to explicitly connect to the SQLite database. And also what we end up with is code that is really tightly coupled with the SQLite database. Now to move to Postgres or something, it's not trivial. Whereas with VDK, we just have to call send object for ingestion, and VDK will handle absolutely everything for you. Sorry. So how is it that we can, like, you know, maybe when we're testing, use SQLite, and when we're using and use Postgres then in production? It's because everything is managed through config files. So here's an example of a config file. In this example, we say that the ingestion method is SQLite, and then the rest is just handled for us. I just want to go back one more time because, so here we do job input, send object for ingestion, and we just include a payload. We, like in this example, we're pulling from a web endpoint and saving it in the database. So okay, so now we know how to ingest data into SQLite using VDK. However, how do we now use the new differential privacy functionality in VDK? Well, VDK is modular and it's highly extensible. So it has the concept of plugins. Plugins are installed like any other Python package. And once they're installed, we can plug them in to the VDK by changing the job. We can plug them into the VDK by changing the job config. Plugins can actually intercept data at many different points in the data streaming lifecycle. For us, we want to intercept the data at the pre-ingestion step, so we can add noise before we send it to the database. So this is the steps you would need to include the apply random response differential privacy to your data. So you would first need to install the privacy plugin, and to do that, you would run pip install VDK local differential privacy, like the way you'd install any Python package, really. Then we would update the config to add the pre-processing step. So here we say ingest payload. Sorry guys, I don't know if I'm always looking away from the camera, but so we would say ingest payload pre-process sequence. And we say, so you know, it's an ingest payload preprocessor. And we say that the name of the ingest payload preprocessor is called random response differential privacy. Now, what we need to do after that is we need to configure the differential privacy random response plugin. And to do that, we need to pass in a kind of a JSON object, which has the table name that we want to apply the random response to, and also the column name. So in this example, the table name is patient details, and the column name is smoker. Okay. Sorry, let me just zoom out. Okay. So we're going to work with this example for a few minutes, which is the smoker example from the previous slides. And I've made it incredibly simple. We're going to generate 60 users, but none of them smoke. So is smoker is false for everyone. So in a loop, create a smoker, save them in the database, create a smoker, send them for ingestion. Looking at this code, we can see that there will be no smokers. However, when the differential privacy plugin runs on the data, we would expect noise, and we would expect that it will return a data set that still shows the frequency of non-smokers to smokers is high. But we would expect it to say some people are smokers. Okay. Sorry. So this is what the results looks like. I ran the differential privacy 3 times, right? And here we can see that it says 45 people are non-smokers and 45 people are non-smokers and 15 people are smokers. And so even like really, if you didn't know anything about it, there was just noise added, you could still say, well, it seems like the vast majority of people don't smoke, which, is good, but we can obviously do a lot better than that. So here we can say, well, even looking at the noisy data, most people definitely don't smoke. But we can move from the noisy data to the real distribution by just applying like a few really common sense rules on the data. The first thing we know about the data is that half of it was pure noise, because anyone who flipped to tails on their first coin flip generated pure noise. We also know that a quarter of all data is yeses that is generated as a result of noise. This would be anyone who flipped a tails and then a heads. So then we can write the formula for the real yeses. The formula for the real yeses would be the total number of yeses in the noisy data, because that's what we have to start with. Sorry. The total number of yeses in the real data, but we have to subtract a quarter of the yeses which has come from random noise, and then we have to multiply that by 2 to account for the fact that half the data is noise. I hope that makes sense. It is intuitive if you walk through it yourself, but I'm not sure if it's coming across here. So what happens when we apply those very simple rules, again, by doing these very simple steps, we can discover the real distribution. Here we can see that this was the data before denoising. So this is the column on the chart on the left. And this is the chart after denoising it. So here we can see that we roughly ended up with 60 people are smokers, and I mean we ended up with a negative amount of non-smokers in some examples. I think that's saying that there's one smoker. This is saying that there's -1, I think. It's actually maybe an error in the rendering. But basically what we're saying is that, after we denoise it, we say that no one is a smoker. So it shows that we can come back to the real distributions. And obviously there is a small margin of error. We want, like the fact that it's saying that there's, that these numbers are slightly off, that's good. We'd never want to arrive at the real distribution just within a small margin of error. But it's easy to see how researchers could pull benefit from getting these numbers. Okay. So next I'm going to go into how to use Unary encoding in VDK. So it's the exact same principle. Again, like install the plugin like we did last time, pip install VDK local differential privacy. And then we want to set again, same field, we're just setting it to a different property where we say ingest payload preprocessor is equal to, and this time we say Unary encoding differential privacy. And then we have to set the field specific for Unary encoding. And with random response, we only need to tell them which column to apply it to. With Unary encoding, you need to give it the finite set of enum values up front so that it can do the one-hot encoding. Sorry. So for Unary encoding, we say the options are A, B, or 0 or O, and then we want to apply this on the column named blood in the table named patient. I'm going to go into an example of that. There's example code here now that you could run if you wanted to see the like get graphs and stuff for the Unary encoding. But fundamentally, it's quite similar to the random response, where you'll see distortions and you can run the aggregate function to get back to numbers that are pretty close to the real numbers. I'm actually not going to dig into this now because it's actually, Unary encoding is way more technical, and it's like, we'll get bogged down in the details because it is roughly the same principle as random response. But if you want to dig into the code on your own, please do, and I'd be more than happy to answer questions over email or Zoom for anyone who wants to dig into them themselves. Okay, so in summary, differential privacy is extremely useful, and if you're collecting data for statistical analysis, you should really consider using it to preserve individuals' user privacy. VDK provides an absolutely brilliant out-of-the-box support for differential privacy. And so even if you just understand the basics of VDK, even if you just understand the basics of differential privacy, you'll be quickly able to configure a VDK instance to apply differential privacy. So what is next for VDK and differential privacy? Well, as I mentioned earlier, there are two different types of differential privacy. There is local differential privacy, which is everything we discussed today, which is what we discussed today, where you always noise the data before sending it to the database. But there's a much more powerful version of it as well called global differential privacy, where if you trust the database owners, you can make much more intelligent decisions about how to noise the data. And you do that at kind of query response time. So again, that would be if you trust the hospital with your medical records, which you have to because you want good advice from your doctor, but you don't trust the researchers outside of the hospital. That's when we would use global differential privacy. And that's one of the things we're going to try work on next in VDK. When you write we will support SQL queries that are provide privacy guarantees using like custom SQL functions. And we're going to even using so that's the next steps. And so if any of this interests you, please take a look at VDK projects, as there are exciting additions being made to it constantly, and we are always looking for new contributors. Like, we'd absolutely love if you would follow the QR code now and give us a star. And also, like, feel free to reach out to me if you have any questions at all. My email is murphp15@tcd.ie. So does anyone have any questions?